Okay, you remember this slide, right? I can walk around and still do this. You remember this thing we talked about that I will come back to this later. So today is that later. We are now going to talk about the truss and a beam comparison. And you remember this, and we said, okay, we will apply the load, and we will have these stirrups here, and they take tension, right? And we were saying that inside, actually, there is an invisible compression field that we cannot see, right? And now we are going to try to find that invisible field and see how we can design the same thing using this concept. First is that you use the bending theory, and now we are going to use the truss analogy or truss and strut and tie approach, because this is not a real truss. There is still concrete in that, right? So, but we are saying that it behaves the same way as if it was a truss. And now we will go into more detail and see when and how we can use this concept. Oh, I forget which way is what. Now you also remember Bernoulli's theorem. We talked about this one. Bernoulli's theorem, which says that if you deform something, if it is a straight section like that one, and if you deform it, it becomes rotated but remains straight. So plane section remains plane after bending. That means there is no warping. You remember warping? We talked about W. So if there is no warping and plane sections remain plane, then we can use the theory that he proposed. And we also said that, okay, that is not really true because there is some warping, and warping is of different kind. And also there is crippling. There is, especially in many other modes also happen. For example, what is crippling? Do you know what is crippling? No, not buckling, really. Anybody knows what is crippling? If you take a piece of paper and you press it, it becomes wrinkled, right? It's not really buckling. It becomes wrinkly, and that is called crippling. So in deep members, we also have the effect of the crippling, and we also have the effect of the warping, and that makes the neutral axis not straight. In fact, there may be more than one neutral axis present because the section is not deforming like this. It is actually doing something like that. So every time it crosses the neutral plane, it becomes a neutral axis. You remember I showed you a neutral plane? There was a diagram. So there is no such thing sometimes that we encounter. So this line may not actually exist. It may go like this. And that, in those situations, this theory, Bernoulli's theorem, cannot be used. Then we also have another theory, Saint-Venant's principle. This says that a localized effect, if you put some if you disturb something, a continuum, with a force, the effect of that disturbance will fade away after some time. So those disturbances do not go too far. They have a local effect, and after some time, they disappear gradually. So this is very interesting for us now to see that even though we know that in some beam the plane sections do not remain plane, but we also can know that those places where they do not remain plane are only localized, not all the way, right? Because that's what this guy is saying. And so if you put a high force here, then after some time the force will become uniform, as if it was applied uniformly, right? At this location, the stress will become uniform. Here there will be no stress or negative stress, tension may be. Here there will be very large stress, and it will go like this and spread, and then after some time, at a certain distance from this location to this location, it will become uniform. This is very important and interesting observation. So now we have two things to look at. One is Bernoulli's theorem, and second is this Saint-Venant's principle. Then it also continues to show that if you put a load there, you will get that kind of thing. And after some time, a section like this one, it will become uniform. Here it will be like that. So this is very interesting and important observation. In fact, when you design a masonry wall or a brick wall, right, and if you put a lot of load on the brick wall, there is a certain angle, you might have read about this or might have used it, after a certain angle, the load becomes uniform on the wall. So the local effect of the point load can be converted into a UDL after a certain distance, right? So by the time the point load reaches the foundation, it becomes a uniform load. So you can divide it by the length of the foundation. You don't design, because the bodies do not deform infinitely, they distribute. The particles, you have a local disturbance, and after some time the particles take the force and then become small and small, and then after some time it becomes as if everybody is sharing the load in the same way. Correct? So this two things, and this is also coming from Saint-Venant's principle, and this is quite important and interesting for us when we go into the details of the Strut and tie model. Alright? Clear about these two ideas? So if I ask a question about this, you will know what is Saint-Venant principle and what is Bernoulli's principle. So don't blame me in the final exam if I ask you this question. You should know basic concepts. These are concepts, and I'm not asking you to remember the definitions word by word, but the concepts are very important, correct? Because these are the basis of our theories and our analysis. So please make sure that you understand these concepts. Then we have another interesting concept, lower bound theorem of plasticity. These are all a little bit new things, right? Or not? Not, you know already about this one.
I've heard.
You have heard about it. Anybody else heard about this one? Anyone else? No. Okay. So for you it's not new. You heard about it, but do you know what it is? Okay. Plasticity. It is, for example, if you were to take a piece of ground, right, and then you walk on it, right, and if the ground is very soft, very bad soil, your feet may go into that one, right, but only up to a certain point. After that it will stop. Of course, I'm not talking about water, I'm talking about a soil, soft soil, but not mud, right? Not liquid, solid, but soft solid. So if you step on it, your foot will go a little bit in and then it will stop. Why did it stop? Because if the stress level of that area has already exceeded and your foot has already crossed the limit of the deformation, how come it stopped? It stopped because the area under your foot immediately was highly stressed. It became plastic, that means it started to flow, but the surrounding areas were not so heavily loaded. So after some large deformation, the load distribute to side or to the areas around that. But what we are saying is that this stress field that you will get of the plasticity, the actual capacity of the medium. So if you now say that you calculate the load, you calculate the capacity of the soil based only on the area of your foot, right? You get a certain capacity, but actual capacity will always be higher than that because of the plasticity will distribute on the sides. So the elastic capacities that you get from that will be higher than the plastic capacity that you have gotten, because plasticity will only make the material flow on a certain location. So it's going to be a lower bound theorem. That means plasticity equations or plasticity concepts will give you the value which will be the least, actual will be higher than that, right? So if you calculate something based on the failure of a certain location, but in reality the actual capacity will always be larger than that. So this is always going to be a smaller So it is a stress field that satisfies equilibrium and does not violate yield criteria at any point, provides a lower bound estimate of the capacity. For this to be true, crushing of concrete strut does not occur prior to yielding. So we'll come back to this particular idea. So just remember that this plasticity theorem that we are going to use, that is going to be the lower bound capacity. Okay, I'll come back and explain a little bit more. Just right now, just remember this is another of the three things that we need to base our theory on. First of all, Bernoulli's. Second one is Saint-Venant, and third one is lower bound concept of plasticity. Then we also talk about the material criteria. How does material fail? What are the criteria that materials can fail? And that is very important for us, because now we are not talking about elastic analysis, we are talking about the ultimate capacity, failures. So we must know how something can fail, like the soil example I gave you. So material can fail, material flow based on Tresca or von Mises criteria or shear flow. Have you ever heard about von Mises or Tresca? Okay. Normally the mechanical engineers know about this a lot. Their entire field in mechanical engineering is based on these two guys, because for them they are using here, they're dealing with a single material. And for example, if you take a steel plate, right, and you put a load on the edge, now if you apply the load, how will the steel plate fail? Because it has a combination of many stresses, principal stresses, tension, shear, many things at the same time. So how will the material actually fail? And for that failure, these two people have developed some equations which relate different stresses to the failure stresses, like the resultant stress that will cause the material to fail. So you cannot find the failure of the material based on only one of the stresses, and you cannot combine them like the elastic theorem. If you combine this stress and that stress and that stress, it doesn't happen that way directly. But that is for elastoplastic materials like steel. We cannot use those criteria because for those materials, all the direction, the stress capacities the properties are similar. Concrete is not like that. In tension different, compression different, shear different. So in this case, we normally look at these failures like failure of paste aggregate in tension, loss of aggregate interlock, crashing of aggregate. So it comes down to finally the failure of the paste or the aggregate at the bottom level. And typically we only talk about the tension and compression in terms of the whole concrete, but inside the material the failure is going to happen, either the stone will break or the paste will fail, right? So that level of failure we normally cannot detect in concrete. So we use it for an average stress concept that you have already seen. Did they show you how to crush the cylinder in the lab? Right? You've seen it, not everybody knows, right? So when you put the load here, it bursts out because of the Poisson's effect. Yeah, thank you. So Poisson's effect. So basically it fails by tension, right? We talked about that. So now I'm just going to repeat what we have already discussed. And we talked about basically principal stresses. I'm just going to go very fast because you already know this, right? I'm just going to say that, okay, we have seen that, we have seen this equation. All of these equations are very good, but the only problem is what? What is the problem with these equations? What is the limitation of these equations? Why I cannot use them now? I said they are very good when we started this course, but now I'm saying they're not so good, right? Why? What is wrong with them? Because they are based on the Bernoulli's theorem, right? Plane sections remain plane kind of thing, right? Now we are talking about materials that do not necessarily go that way, right? So that's why we have to now talk about some other things. We also talked about shear, and we talked about if you have shear, it produces compression and tension, and the thing fails with in the tension direction, and we can put a stirrup there, and we can stop the shear failure by adding reinforcement. It takes all the tension, correct? So I'm just repeating what we already discussed so that you understand where we are now. And I also told you that on a beam we have many locations. Stresses change at every location, and this diagram keeps rotating in principal direction. So we have all these combinations, and I was telling you at that time that it's such a waste of time to calculate the concrete capacity in shear because it's too small and it changes all the time anyway. So now is the time to come and say, okay, let's throw that away. Let's not do that anymore. Let's not worry about the concrete shear capacity. Let's not worry about the concrete tension capacity and see what happens, right? And let's not worry about this equation and all the equations that you people helped me to find from the code. Remember all these equations, one of the assignment, to find all of the concrete capacity equations. So now we're saying they're useless, right? That was before midterm. After midterm, now they're useless. Because we are going to study a new class of problems where these equations will not help us. And one of the main reasons is that those are not governed by the theory that we have been talking about so far. Okay, so we were saying that finally, we only deal with direct tension, direct axial stress, either tension or compression, right? Because shear produces tension and compression from the principal stresses. So if we come to that conclusion, that means we come back to the truss, because truss has only compression and tension, correct? It has no shear. And if we use that logic, then the question that I raised last time, and I want to continue is that when we design the concrete beams, for designing for bending, our first assumption is that concrete takes no tension. So all the concrete below the neutral axis is neglected. But when we design for shear, we take the small tension capacity and try to calculate the concrete shear capacity, correct? And we were saying that, okay, this is not logical, because in the same beam, one stress for bending, we say concrete cannot take tension. Another stress for shear, which is also tension, we say it can take tension. So let's make a uniform criteria, and we say ignore all concrete which is in tension, because it's very small anyway. So that means all of the concrete in a beam which is in tension is effectively removed from calculation, and all of the concrete which is in compression, we only keep that part, and all of the tension is given to steel, all of the compression given to concrete. Do we all agree on that? Right? Seems logical. So if we agree on that, then we can come to this idea, truss analogy of concrete members. That means the concrete member is no more than a truss, because it can only take tension and compression, tension taken by steel, compression taken by concrete. There is no shear, right? So shear disappears. There is no torsion, because torsion produces shear and axial forces, so torsion disappears, right? So only what we are left with is tension and compression, correct? Isn't that simple? So if we can use this concept properly, we can simplify very complicated problems into very simple solutions. And that was the basis for this thing that I showed you last time, and now we will move on from there. So this Strut and tie method is actually a unified approach. It unifies, last time we talked about unifying concrete columns and beam, and we unified those kind of things, and now we unify everything, all 6 actions: bending, shear, torsion, all kind of things we unify into one approach. And we say, okay, the entire capacity of concrete member in certain situation comes from tension and compression, tension taken by steel, compression taken by concrete. End of story, right? If we make that assumption, then we come to the idea of the strut and tie model, in which we can resist all forces. And This is a very useful and rational approach, and this is a lower bound approach. Actual capacity will always be more than this capacity. Why? Because concrete does take some tension. So that tension capacity of the concrete will be added as an extra factor of safety for us. And we are saying that we are ignoring all the concrete in tension, but actually the concrete is still there. So it's going to take some forces. So that means this assumption that we are making is a lower bound safe solution. We cannot go wrong with this. It is not unsafe to assume that all concrete in tension is gone and all compression is taken by concrete and all tension by steel. But actually steel also takes some compression, correct? Concrete also takes some tension. So our assumption is on the safe side. So if we use this method, we come to a simple solution yet safe, right? That is what we call lower bound. And this one we can then go on to see. The subject was first presented by, even before that. This Slide in 1987 and also continued in the text by Collins and others, but actually that is not really true. If you go back very far in 1920s, there was a paper by one guy who said this, but nobody believed him, and the poor guy passed away. And after his, long time after his death, now people say, oh, he was right, right? And then later this slide from Germany, he is the one who refound that paper and restarted this whole process again. Actually, the main guy who started this was Leonhard something, right? Also from Germany. He had a very old book I saw somewhere, and he had presented this concept, but it never adopted. And ACI and ASHTO start to believe in this in 94 and 97, and now the latest up to 2000 they start to believe it in more. And so the codes were the last one to obviously believe in. So basic concept is very clear. The section is assumed to be fully cracked, even though it may not be cracked, but for our purpose we assume the section is fully cracked. All tension, all material, all concrete tension is gone. The compression is taken by struts, all tension is taken by ties. Ties and strut provide a stable mechanism, and this is a lower bound solution. So please remember this concept, right? Everything in this one is kind of true or a safe assumption, correct? Application of this approach is post-cracking shear behavior in design of beams and shear walls, design of corbels and brackets. So, what could be the drawback of this method? Seems too good to be true, correct? So simple, there must be something wrong with it. What's wrong with this method? There's always something wrong with simple things. What's wrong with this method? It seems very logical, everything seems to be correct. So why we cannot use it all the time? Why we use it only sometimes? What's wrong with this method? For one thing, this is based on the assumption that the concrete is already cracked. So we do not know what is going on before cracking. So service level behavior cannot be determined from this mechanism. It is only good to calculate the final capacity of the section for ultimate response, but it does not help us to say anything about the deflections or anything about the pre-cracking or vibration or crack control, because we are saying that the section is already cracked, correct? You tell a client that has paid you a lot of money that your beam is going to be cracked, he will take the project away from you because he's not an engineer. They don't expect the structure to crack, but here you are assuming that the concrete is all cracked, right? So that means serviceability is not satisfied here in this approach, and we must do some other checks to make sure that the serviceability is satisfied. So this is a good check on capacity to prevent failures, but it is not a good method to design for serviceability, for crack control, for deflection control, for vibration control. All of that cannot be done by this method. That's drawback number one. Okay. What is another drawback? You will see later, that we will talk about when we go. There is one more drawback that we will talk about. This is another paper in 1941, long before this current Strut and time model, in which they talked about micro-truss models to understand the concrete behavior at that time. Because by hand, truss is easy to solve, right? Finite elements were not available, things were not available. So people at that time, people tried to make things simple and try to create a micro-truss model of all of the things which is happening inside the concrete. And later, this developed into the method that we are talking about. So basically, if you take one element, then we say there is an angle, and based on that, there is a tension and compression, and there is a truss, double diagonal truss, which is holding this. Let's say, okay, this one here. If I was to calculate, you know the apple there, if you bend it, it bends the new one, right? I don't want to try on my phone. But if I was to try and find out what is the stress in this glass, right, whether it will break or not break, if I want to do this, I need a finite element program to calculate the stresses in this one. But on the other hand, if I assume that there is one, these are all pins on the corner, and there is two diagonals inside, and when I'm going to bend it, one of the diagonals is going to be in tension, one of the diagonals is going to be in compression, then I can find approximately the stresses inside this area. I can find the force in the middle of this plate, otherwise which will be not possible, right? So we can create this micro-truss model of a continuum by putting hinges or pins at the corner and putting diagonals and say, okay, now I can find the forces between them. And if one of them is tension and I say tension concrete cannot take, then only one of them remains. Compression can only remain, right? So this, we still use this idea in modeling of the masonry walls. If you have a wall inside a building, right? And how do you model a wall? It's too complicated, using many types of elements. It's too complicated behavior. There are many bricks there, there is mortar there, so many things, you can't model it, right? So normally, the codes and these methods, we say, okay, you can replace a wall by a diagonal, equivalent diagonal. That means the entire wall is replaced by an equivalent truss element, right? So this concept now of using the Strut and time model has become very useful for us to reduce complicated model into simple models comprising only of tension and compression. And we can make them nonlinear, we can make them many things, right? So this idea originally, which was used to make things simple for hand calculation, has come back to help us in modeling using computers, because sometimes we still cannot use the real structures because they're too complex to model. So we convert the real structures into equivalent truss system and then put them in the model and use the computer to calculate the forces in the trusses. Okay? We'll come back to this again and again. So this micro-truss model or micro-truss concept has been there for a long time, and it has now been revived and now being used in the truss model. So this is what people used to do. You want to find out how the stress pattern will happen in this one, you divide the whole thing into a lot of small trusses, and then you start from one point, from there's no pointer here, you start from that point of where the load is applied, and then you can see over there that there are loads there. If it's a load, then from there you can say, okay, I have to, this load that is coming down can go into two directions. You can then after that go to the next node and keep on distributing it until you can find all of these stresses, right? So this idea of using these micro trusses or micro elements was originally used and now can still be used to calculate the stress state inside an element. Of course, many people will say, okay, you can use a shell element or you can use a membrane element, infinite element, which is true also. But what is the problem? Shell element and membrane elements have the same behavior in tension and compression. So they cannot model concrete well. Concrete can only take one direction stresses, not the others. So you can use the truss model to model the materials more reliably, especially for the failure levels. So basically elastic level and failure level are two different things. Before cracking, concrete behaves differently. After cracking, concrete behaves differently. We know that. Before cracking, it is just like any other material. Steel or rubber or plastic and concrete, they are the same before cracking. After cracking, no longer the same, because in one direction it takes no stresses, in other direction it takes the stresses. So that is why reinforced concrete is a complicated material, because it suddenly changes behavior once it starts to crack. So we can analyze it at two levels. Before cracking, elastic model, that's what we do normally. And then the second model in which we say all cracking has already happened. Intermediate we don't know. That is too complicated. There are ways to do that, some people do that. There are many software which can handle that, but not practical. So we can deal with two states. Just before cracking, one material, elastic stress distribution, elastic equations, and after cracking, post-cracking situation, all concrete and tension gone, only concrete and compression remaining, all tension taken by steel. So now we have two methods to evaluate deflections and other things. Cracking we can do from here, and strength we can do from this side. So now we are dealing with strength that we use the Strut model. So as a result, this model can capture shear and everything, because it talks about stresses, not talks about the stress resultants. So from there, internally we can calculate what is happening inside. And same micro-truss model can be converted into bigger truss model, you will see later. Right? So these are the limitations. Of course, the first one is not a limitation, actually that's a good thing. The theoretical basis of the truss analogy is the lower bound theorem of plasticity, which is a good thing. So that's not really a limitation, we just know that okay, this is a lower bound solution. Second one is, however, concrete has a limited capacity to sustain plastic deformation, and it is not an perfectly plastic material. So that means cracking, large cracking, we cannot predict what happens after that. Because once we give all the tension to steel, steel can yield easily. So what is happening in the concrete then? We don't know. Concrete cannot just let the steel yield and stay quiet. It has to also deform with that. So we do not know the large deformation, this is not good. Ashto, you know what is ashto? Right? Yes, no? Anyone who knows what is ashto? For? Roads. Yes. Basically, it's for roads, right? Highways. Okay. And they do all the bridges and everything. So ASHTO is one of the important codes that if you use doing bridges and highways, you will use this one. And what is RRFT? Road resistance. Correct. So that method is quite popular. Adopted the compression theory to limit the compressive stresses. So what they have done is that to limit, this is quite interesting, that to limit the deformations and capacity of a Strut model which can have infinite capacity, they base it on the compression capacity of concrete, because the tension capacity of concrete is related to compression capacity of concrete. So if you can limit the compression in concrete, indirectly you limit the capacity of the whole thing, so it will not fall down, right? So that is what they have done, that because all compression taken by concrete, if you limit the concrete cannot take a certain amount of compression, then obviously you limit everything else, because that's part of the model. So that is one of the ways to control or overcome the shortcomings of the Strut and tie model is that you calculate the stresses, the forces, no sorry, forces, and after this you say, okay, concrete part cannot take more than this one. Because concrete cannot take more than this one, then because of the equilibrium, steel also cannot take more than a certain amount. Okay. I know many things are not making sense to you right now. When we go to actual applications, we will understand these concepts again. This is the definition adopted by the ACI. They adopted very late, but they adopted, as you can see in 11. Strut and tie is a truss model of a structural member of D region. So now they are trying to be safe. They don't want you to use this everywhere because otherwise their whole code, all part of the code will become redundant, right? So they say no. Only for D region you can do that, and we will see why. In such member made up of strut and ties connected at nodes, capable of transferring deflected loads to supports or adjacent B regions. I will show by diagram what they're saying. Okay, so basically ACI is limiting the use of the strut and tie model, not to all members, but parts of the member or members in which the D region is governing. You remember the D region? Yes. When we started teaching this course long time ago, 10, 12 years ago, the code did not allow this. So we had big problem convincing people to use it. Because we knew that this is good, but the code will not have it. Then first it became an appendix in the code. And gradually it moved to the main code body. So now it's fine. So now we can use it with confidence. This is the plane stress problem. I don't want to. I think Dr. Panchit is dealing with this or not yet? Not yet. Okay, next course. So let's skip this one for now. It's quite relevant. I don't want to confuse you further. Okay, coming back now to the application. So that was the background, right? Let's now see a little bit now reality. What's really going to happen? Why and how we can use this. This is a beam, and as I mentioned to you last time, this portion is D, this is B, and this is D. Here, ACI says you use a certain equations that we have studied before midterm. All of that you have studied, shear, torsion, flexure, everything so far applies to blue region. Does not apply to orange region. And whatever we are going to study now is going to apply to orange region, not apply to blue region, according to ACI. But I disagree. That concept that we are studying actually can be easily extended to B region and D region consistently. There is no problem with that. Okay? And we will argue why we can use it and why ACI does not want you to use it. We can also argue that. But later, one of the assignments you will do is that you will compare the design of a beam using the ACI normal method and using the strut and tie method, and you will hopefully find that there is not much difference, right? So we'll talk about that very soon. But let's for now assume that we are going to use this approach. This is another way of looking at the same beam that we have shown, and those are the stress trajectories drawn by using the principles tension and principal compression, principal direct, and you can see from here D region, D region, D region, D region, B region. And now we are relating this size of the regions with the what is D small d? Depth, right? So now we are trying to see what is the extent of the D regions. This brings us back to which principle? That we should. In the morning we just studied Saint-Venant principle. which says that the disturbance is local and about the size of the member or 45-degree angle or something like that is where the disturbance will die away. So that gives us the idea of the D and this. So D and D, 45 degrees approximately, is the starting point of our definition of the D regions. That after that, the stresses will become uniform, so we can treat them as normal. But in that portion, they are not uniform yet, so we need different methods. So you can see from there, D, D, D. So point load, any concentrated load, any disturbance that we see, what we saw in Saint-Venant's principle, that effect will be limited to a certain zone which is related to the dimension of the member or 45-degree angle, right? And after that, it becomes uniform. So that way we can decide which portion is D and which portion is B, right? So this one is deep beam behavior, and this one is slender beam behavior, and out of that is also there's a D region, and also there's a, this is interesting. This is deep beam behavior. Why? Deep beam definition is that if most of the length of the beam is D, it's a deep beam. Normal beam definition is that if most of the length is in B, it's a slender beam or normal beam. Here you can see 3D is B region, 2D is D region. So 3D is more than 2D, right? So it becomes a normal beam. Over there, the entire length is in disturbed region. So now the question is, what about a beam which has 2D in B and 2D in D? What is that? Is it Bernoulli's? It's a normal beam or it's a deep beam? Both, right? That's exactly right. So it's actually borderline. That is where we decide we can go either way, right? You can choose to use it as a deep beam, or you can choose to categorize it as a normal beam, right? But after that, it becomes quite clear. So before that also quite clear, after that also quite clear. That is a gray area. All right. So we will see that how we are going to deal with these by using our newfound tools. These are people have been trying to create those stress trajectories, and you can see that the lines become parallel when they become far from the supports or disturbance, and close to that their lines are disturbed. So these are, people have been trying to do this in many ways, by testing, by stress analysis, by trajectory analysis. But you can see from here that, okay, if you look at a typical frame like that, this is how it could look like. So D region actually is quite common, more common than you would imagine. Except for a simple beam, in a real structure, there are many portions which are D, 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 D. So that means we need to deal with these portions with a proper design method, which normal design that we have studied so far will not handle. Okay? So basically we are talking about foundations, footings area, brackets and corbels, joints, openings, concentrated loads, supports. Right? So all of these areas that you can see from this diagram need a special attention, or is the area where you can use the Strut and tie model as a alternate design tool. Clear? So if we know now this, let's see how we can do this. And again, this is coming back to the old idea that we discussed about the angle of the strut, the cracks and angle of the stresses, and then the tension angle and the compression angle. You have seen all of that, right? But in our case now, things will be much simpler. Why? because we don't worry about cracks anymore. We assume already that everything is cracked, and we don't care what is the direction of the crack, where is the crack. We just assume that the entire beam, wherever there is tension, is fully cracked and concrete is gone. Only compression is left, and all tension is taken by steel. So that means we don't need to worry about these things anymore. So we are going to make it very simple. Wherever there was crack, wherever there is a tension, it's all gone. Right? So shallow members, for which our normal beam design theory applies, is a member where most of the beam length is B region, correct? If you are going to have closed book exam for final, some of the questions will be from this slide or similar slides, okay? That you will get a sketch and they will ask you mark B region and D region, okay? Or define which is deep beam or not deep, something like that. Deep members are where most of the beam length is in D region. We already talked about this. Thin members and thick members. Many people get confused about these four terminologies. Deep and shallow, thick and thin. Not the same. So thick member doesn't have to be deep. Thin member doesn't have to be shallow. Thin member is flexural deformations are predominant and shear deformations can be ignored. Thick member is shear deformations are significant and cannot be ignored. We talked about shear deformations last time, right? So when you bend something, it is a summation of the two deformations. Some portion of the deformation is coming from the elongation of the fibers below and elongation of and shortening of the fibers above, which is flexural deformation, and some is coming from the shear angle change in each section, right? So if the beam is very flat, very small, if you bend it, most of it, the deformation will come from flexure because that is a weak plane, weak direction. So it will be different. On the other hand, if you have a very thick plate like this, okay, like this, and then if you try to bend it, then the bending stiffness is very high. It cannot bend anymore because the moment of inertia is too high, right? d cube over 12, right? So that means if the depth is increased, this flexure stiffness not increases by, right? It increases by cube. So that means it will become very stiff and it will not deform. The axial stresses will be too small to cause. Then the shear deformation, which is related to only one D, will become more predominant and it will be more important. You cannot ignore them. So that means if a beam, if a member is high and short, shear deformations cannot be neglected because they will be larger part of the total deformation. If the beam is very shallow and long, shear deformations, although present, will be a smaller percentage of the total deformation because bending is too soft, right? So thin members, thick members, these are two different things, and shallow members and deep members are two different things. Definitions are different, application is different. This is applicable for the finite element analysis formulation of the elastic deformation theory. This is useful for the post-cracking mechanism or post-cracking strength, right? Although a deep beam may be a thick beam, but not necessarily. Rules are different. One is based on the B and D region, which is based on dimension. The other one is based on whether shear or flexural deformations proportion, right? So it's a confusing thing, and that's why one exam question will be from this slide. So please do understand the difference between these four terms. So that is the definition of a deep member. Member in which most of the length is D region, members that do not follow the ordinary flexural theories, and members in which a significant amount of load is carried to supports by a compression strut joining the load and the reaction. These are some of the definitions of a deep member, right? Deep beam, walls, shear walls, footings, pipe caps, brackets, many things. Also, we talked about this one, non-linear stress distribution, possibility of lateral buckling. These are the issues with deep members that we normally do not encounter in normal members. High stress at supports and load points, reinforcement development and anchorage, very sensitive to differential settlement, and very stiff elements. So these are the special characteristics of deep elements, things that you normally do not encounter in normal members, right? And when we design deep members, we have to consider all of these, and we will come back to them when we talk about the deep members like transfer girders and many things like that, right? So nonlinear stress distribution, high stresses at supports and load points, we have seen that. Reinforcement development anchorage, we will talk about that when we talk about the ties. Very stiff to very sensitive to differential settlement, obviously, because stiffness is so high that even a small deformation will cause a lot of bending moments. Correct or not? No. Now you're confused. How is that possible? If the beam is too stiff, why is the problem? The problem is very simple. If it is paper, can I have a paper? Okay, paper like this one, right? So no stiffness, I can bend it easily, right? No problem. So if I do like this, there will be hardly any stresses. The paper will just deform like that. If I do it like this, now if I try to bend even a little bit, it cannot. So very high stresses and many moments will develop because the stiffness is so high, and deformations are related to stiffness, correct? So small deformation produce a lot of bending moment. If it's a beam like this one, very rigid beam, right? Moment of inertia is very high, I equal to d q by. To produce very small deformation, you will need a very large moment, correct? To make a small deflection, you will need a very large moment. True? Then compared to this one, correct? Very small moment can do that. Reverse is also true. Small deformation, small deflection here will produce very large moment. Correct? Because the two have to be balanced. Here, large deflection, no moment because stiffness isn't there. So that is why large beams or deep beams are very sensitive to small deformation because they produce very large moments in the member. Okay, I think we should stop here. We will continue tomorrow.